Hello from Hanover Messe in Germany, and welcome back to Technology Now, a weekly show from Hewlett Packard Enterprise where we take what's happening in the world and explore how it's changing the way organisations are using technology. This week, it's just me, Michael Bird. Now, for those tuning in to the audio version of this episode, you probably can't see that I'm currently sat in what I've been told is a hot tub, but it's basically a bath. And I'm surrounded by industrial equipment and data center equipment. And if you want to see for yourself, just search for Technology Now on YouTube or Spotify if you want to watch the episode. Anyway, in this episode, we are looking at how excess heat energy generated by data centers can be repurposed. We'll be exploring how much waste heat is given out by our infrastructure, and we'll be looking at how you can capture this currently wasted energy. And we'll be asking what can be done with this new energy source. This pool that I'm currently marinating in might be a little clue about one of those uses. So if you are the kind of person who needs to know why what's going on in the world matters to your organisation, this podcast is for you. And if you haven't yet done so, do make sure you subscribe on your podcast app of choice so you don't miss out. Right, bubbles are on. Pool's just the right temperature. Let's get into it. Excess heat is a huge waste of energy. A 2023 white paper from Danfoss found that the EU alone released 2,860 terawatt hours of excess heat per year. And we'll link to that stat in the show notes. Now, that's an incredibly high number, which is pretty difficult to visualize. However, according to our producer, this is enough to make every person on the planet over 12,000 cups of tea. Around 33 every day for every person. Spot the British person writing those stats. But where is all that excess heat coming from? Well, it comes from basically everything. Pretty much every process gives out heat somewhere, and the more inefficient the process, the more waste heat is given out. Your laptop probably gets hot if you're running too many applications on it at once. Your fridge may feel cold inside, but that's because the heat from inside the fridge is being pumped out. If you stuck your hand behind it, you probably feel quite a bit of heat. And if you've ever had to change a light bulb and it was burning hot when you touched it, that's excess heat. It's everywhere. Now, in a lot of cases, it simply isn't worth collecting that heat energy. Your laptop isn't giving out enough to do much of anything really. But what if we could scale that up? Let's think about the data center. According to a 2024 report from the International Energy Agency, data centers accounted for 2% of the global energy usage, and the amount of energy they needed is predicted to double by 2026. That is an incredible amount of electricity. But with all of that electricity needed to run the data centers comes a lot of heat being pumped out of them. Currently, this heat is being dissipated into the environment. But what if it could be harnessed and put to good use? Now, the technology that turns the heat being blasted out of a data center rack into something that's actually useful is pretty cool. And earlier on, I met up with Malte Matthies to find out a little bit more about how they take heat from a data center and transform it into heat for my hot tub here. So we are stood in front of well, there's a whirlpool bath with some bubbles. There's some industrial equipment here, and then there is this. I would say it's a server rack, but it's not a server rack I've ever seen. And there's lots of red and blue tubes. So can you just explain what's going on? What are we looking at here?
On here, we are looking on a Cray high-performance computing rack. So it's
right.
the EX series. That's we call it internally the big beast. So that's the one with the highest capacity currently. So for AI workloads, that beast has a 400 kilowatts capacity. For these workloads and that density, you need to have water to cool it, because pure air, like usually you have like the fans running air through the server, that's not going to fly anymore. So, and therefore you have here the blue and the red ones, that's the water connection directly to the server blades. And then they are consolidated over there in that nice piping. So that's the water flowing through the system, through all components, and cool them down without any fan in here. So that's 100% direct liquid cooled rack.
Right, okay. So, and I'm assuming if these were fans, then we wouldn't be standing here. It'd be quite loud.
No, no. And you would have to, like sort this capacity into at least 8 racks to cool them.
Because it looks very, very dense. They're so closely tucked into each other, aren't they?
Yeah, that's what I mean by 400 kilowatts. That's like currently the highest density in industry. And HPE, we're the only ones offering pure liquid cooling on that density.
And when we're talking liquid cooling, are we just saying it right here? Is this just liquid cooling the processor? Is it liquid cooling the memory? Is it liquid cooling a combination?
In this one, it's everything. There's no fan left, so it's 100% purely direct liquid cooling.
Okay.
We have one series below, HPC series, that is, we call that hybrid. So you still have the largest portion direct liquid cooled, like you said, like the processes and stuff like that, but still a portion of 25-30% needs to be air-cooled as classically in data centers. So the one, let's say one series below, that's around 150 kilowatts in a rack. That is hybridly cooled, still with a bigger direct liquid cooling portion. But and then the ones below, it's classical air cooling.
So it looks like the water is coming in and out, hot and cold water, into this thing. So what's going on here?
That is the CDU, a cooling distribution unit.
Right.
So you have this one, which is circulating the water coldly into the blue ones and red warm out. And that can host 2 of those, so left and right. And then you have here like pumps, and that's circulating the water. And you have here the possibility to kind of transfer the heat out of that inner circle into another one, which you can use or you have to use in the data center. Then.
Okay. So usually with an air-cooled server, an air-cooled data center, it kicks out hot air from the fans, and then you basically just try and cool it with air conditioning to keep it cool.
However you do that, you try to bring the heat exchanger as close as to the air-cooled rack.
Sure.
So whether it's going to be an water flooded back door or a side cooler or air conditioning in the room, but you're bringing the warm heat, the heat out of the air into a media that's liquid. And then you transport it through your data center. And usually, classically in all data centers, you spend some more energy to just cool it off in the air.
Yeah, okay.
So, and that's, from our perspective, massively wasted energy.
And so what we have here is we're taking excess heat from the data center through a heat exchanger, and then we're doing something useful with that heat.
Yeah, that's an example of usefully, right? So, usually what we offer is really district heating. Okay. So you're trying to heat your buildings around the campus, all of that. You also could use it for urban farming, so greenhouses, fish farms, whatever. Or use it for processing heat, so industrial use that needs hot water. You can use that, bring it up by a heat pump a little bit more in temperature level, and reuse it.
All of this waste energy, all this waste heat is coming from the data center.
Yeah.
So what we're talking about here is running AI models, AI, large-scale AI workloads.
Yes.
And that uses a lot of energy, a significant amount of energy, from what I understand.
Yeah.
And are we saying that actually, like, air cooling that is nearly impossible, if not impossible? And so are we saying that water cooling is the future? Like, you won't really be able to air cool those sorts of workloads?
What we see is that first, just for Europe, it is predicted that the energy demand for data centers in the next 5 years to 2030 is going to triple.
Wow.
Driven by AI workloads. So, and as I said before, currently all classical data centers are air cooling, take the heat out of the building and release it to the environment. And we are saying that's really a massive waste of energy.
Yeah.
Because you have paid electricity to run your workloads, and then you just release the heat out in the environment. So why not reuse it? You have it anyways, right?
Yeah.
So, and this is what we're showcasing here is, and we can do that in our modular data centers. So we try to pack it pack it in containers, and then you can bring those containers, that data centers, wherever heat is generated or heat is needed, and also where possibly renewable energies are generated. So you can bring the data center where it makes sense from a wider perspective than just running IT.
We will be returning to Malta in a little while, so stick around to find out more about how we can harness the vast quantities of energy being pumped out by data centers later in this episode. Right then, now it is time for Today I Learnt, the part of the show where we take a look at something happening in the world that we think you should know about. And it's been a huge week for dinosaur lovers as a new specimen of the two-clawed dinosaur has been discovered, this time in the Gobi Desert in Mongolia. Now, the fossils were unearthed back in 2012 and were immediately recognized as a therizinosaur. However, it's only recently been revealed to be a new member of the family. Researchers were initially struck by the difference between this new dinosaur and the therizinosaurs, already known as the new specimen, appeared to be missing a claw instead of the usual 3. It only had 2. Now, I'm sure that the majority of people have no idea what a therizinosaur looks like, so I'm going to try and paint a picture. Imagine this, a cross between a T-Rex and a giant sloth. They're a type of theropod, like the T-Rex, but with a much smaller skull. And these huge, curved claws, which they would have used to grapple branches and trees when eating or slashing at foes during battle. Right then, let's jump forward in time and dive back into my interview with Malte, which will, I hope, give us a little more information about what I seem to be presenting while I'm sat in the bath. So what sort of examples have you got of where this excess heat can be used? I mean, we have the pool example behind us.
Yeah.
But not every office has a pool. But every office should have heating, although then perhaps some countries where maybe, warmer climates where you wouldn't have heating.
You can generate cooling out of heat.
Right, okay.
So that's technically possible. It's just another amount of energy, but you can do that. You can heat your building. You can generate warm water, to wash your hands or shower or whatever.
Yeah.
You can use it on a campus for universities. It's not just one building, because just imagine, for a larger cluster, we are talking about megawatts of load, not just one rack, megawatts of heat. You need some more offices than just one, right? So, and therefore, our examples are heating systems, district heating systems, campus heating. Use it for your building or the buildings, but also maybe use it for your production, where you need hot water, steam. You can use that water, bring it up with a heat pump and use it. Or use it, for example, for greenhouses, fish farms, urban farming. So there is plenty of use cases that need heat energy. So in the end, the use case gets really interesting if someone who operates those data centers, driven from IT perspective, resells the heat. It boosts your business case because you can monetize that in the end.
Absolutely, yeah. Yeah, because I guess some offices won't be heated in the summer.
That's the usual question. It's like, we can use our buildings. And we were like, you can do that, but what you going to do in the summertime?
Yeah.
So exactly, you can generate cooling, or you find a larger one where you have like a flat usage or demand on heat over the year. Okay,
so this device allows us to utilize the waste heat from the data centers. Can you just sort of explain in a bit more detail how the heat is transferred from this water cooling loop to actually do something with it?
Yeah. So in that inner circle, we call it direct liquid cooling. It is water, but there is an additive in there. So it's not pure water. It's 75-80% water. That's circulating, and on these machines, the temperature level output is close to 50 degrees Celsius.
50.
Wow.
50. That's
exactly,
hot. That's
right?
warm. Yeah. Okay.
So that's pretty warm. And then you circulate that, and you transfer it over a heat exchanger into a secondary loop.
Okay.
And from there on, you can use it for whatever you want. So, as again, in classical data centers, you would just cool the second loop by, an air cooler outside to release it in the environment. Or you take that energy in the water and reuse it for your bath, for the heating, for processing, for urban farming.
So it's not, like it's pretty simple to explain.
It sounds
pretty simple.
Yeah.
I guess there's more to it.
The devil is in detail. So
there's lots of pipes and switches and
so
gauges.
We do that in co-development and cooperation with Danfoss a Danish company that's very specialized in exactly those technology. And by the way, the fun fact is they operate a modular data center from HPE on their headquarters in Denmark. Okay. And from there on, it was jointly developed that this heat recovery modules, also in a kind of standardized way, it was jointly developed, and Danfoss use it is already at their headquarters.
Yeah, okay. But I imagine there are lots of instances where our office buildings have racks of switches, maybe racks of some servers. Do you see this only being something that would be used for very high performance computing?
Yes, so the very big beast for it, that's from there on. One downgrade, the Cray systems also are water cooled, direct liquid cooled, and need some air cooling. But we also have our ProLions now already with direct liquid cooling option. Okay. So it is going down into the legacy world, and we're expecting that this is becoming the new standard over the next generation.
Are these connectors, these standardized connectors, like could you see an environment where you'd roll a rack into your building's, server room, data center space, and there are just, ports on the other side to connect it into your building's heating system?
On one hand, yes. On the other hand, that's still, it needs to be, secure. That's very heavy. Find a data center that's 3 tons plus. So find a raised floor that works with that. Yeah. So there are some challenges, but nevertheless, we see that as the future of IT, because the density is getting higher and higher. It's more consolidated and more consolidated. So there is, from a physical perspective, no other chance than do it direct liquid cooled.
Because I guess practically speaking, this is using a smaller footprint as well, less space.
For what you have in there, that's that's like the most condensed footprint in industry.
What would be
Once again, just look at this. This is double rack, standard double rack size. And that's like, again, I need to say it again, 400 kilowatts in one rack.
Yeah, it's a lot.
And NVIDIA just released the next generation, so it's not going to get down, it's going to go up.
Yeah,
the next one is probably 600 kilowatts.
Wow, okay. More density. So what's the future here? Where do you see this technology going in the next 5 or 10 years?
Speaking about a shorter term of 5 years, for example, so what we expect is that this workloads with direct liquid cooling is going to develop to a new standard. So we offer with our containerized data centers, our performance optimized containerized data centers, the pods, we offer also purely liquid cooled solution. You can bring the workloads where on one hand energy is generated, or on the other hand the heat is taken. So it's no longer classically London, Frankfurt, Amsterdam as the hubs. So data centers can be moved around, and our vision is to make that, bring it into masses. Heat reuse as a classical standard of data centers.
Yeah, and it becomes something you consider with a data center, whereas previously it's not.
It's not a standard, even if regulation tries to drive that.
Yeah.
So there were before. It was economically, so from a business case perspective, it doesn't make sense. If you have 20-degree water out of an air-cooled system to bring it up, you spend too much energy in heat pumps. Now we have 50 degrees, so that is hot.
That's good, yeah.
So that works now, and the business case works. And on the other hand, the machines itself, the chips, need it to be cooled.
Yeah.
So it's being driven from two sides.
Do you see any regulation coming in, maybe from governments, to say, actually, if you're going to build a data center, it needs to be liquid cooled, and not only does it need to be liquid cooled, you need to tell us what you're going to do with that excess heat?
So the European Union has released an energy efficiency directive, and for example, I know that from Germany it is mandatory to offer heat reuse capability if you want to build a new data center. So you cannot do that without. You need to do that already. So yes, that's regulatory things are accelerating that, yes.
Thanks so much, Malte. It's been great to hear from you, and it's exciting to get to experience one of the potential ways we can do something with all that waste heat being pumped out of data centers, especially if they're only going to be getting bigger in the future. And if you want to find out more on the topics discussed in today's episode, make sure you check out the show notes. Well, we are getting towards the end of the show, which means it is time for This Week in History, a look at monumental events in the world of business and technology which has changed our lives. Now, the clue last week was it's 1932, and you know what they say? When life gives you lemons, isolate compounds. Now, I thought this could be something to do with making a battery out of lemons, but it turns out I was barking up the wrong tree with that one, because it turns out it was the discovery of vitamin C by Charles Glenn King, who isolated the compound in his laboratory and concluded that it was the same compound as the hexuronic acid, which was being investigated by the Hungarian biochemist Albert Szent-Györgyi. Now, both King and Szent-Györgyi had concluded their research on guinea pigs, which, like humans, aren't able to make their own vitamin C and have to eat it as part of their diet. Now, it's okay if you aren't the biggest fan of citrus, because you can also get plenty of vitamin C from leafy greens. After discovering the compound, King would go on to prove its ability to combat scurvy, leading to the renaming of the compound to ascorbic acid, which literally means anti-scurvy acid. Pretty cool. In the end, Szent-Györgyi would go on to be the sole winner of a Nobel Prize for the discovery of vitamin C, despite reportedly long and acrimonious deliberations on the committee. Anyway, the clue for next week is it's 1918 and the United States is springing forward into a new age. Springing forward into a new age. Not got a clue. Hopefully we'll find out next week, so make sure you tune in. And that brings us to the end of Technology Now for this week. Thank you so much to our guest, Malte Matthies, and of course to you. Thank you so much for joining us. If you've enjoyed this episode, do let us know. Drop us a review or comment wherever you listen. Technology Now is hosted by me, Michael Bird, and this episode was produced by Harry Lampert and Izzy Clark, with production support from Becky Bird, Alicia Kempson-Taylor, Alyssa Mitri, and Natasha Nike. Our social editorial team is Rebecca Wissinger, Judy-Ann Goldman, and Jacqueline Green, and our social media designers are Alejandro Garcia and Ambar Maldonado. Technology Now is a Fresh Air production for Hewlett Packard Enterprise, and we'll see you at the same time, a slightly different place. I won't be in a pool, but we'll see you next week. Cheers.